Hey, welcome to the Explainer. Today, we're diving into something truly elegant, one of the cornerstones of physics, Gauss's law. You know, it's kind of like a superpower. It's a tool that lets you see the invisible and figure out what's inside a box without ever opening it. So let me start with a puzzle for you. Imagine there's this box, right? You can't see inside, but you know there's some electric charges in there, and they're creating this invisible field that's just flowing out. Now, how in the world could you measure the total strength of that outflow without cracking the box open? It sounds impossible, doesn't it? Well, spoiler alert, this is exactly what Gauss's law lets us do. Okay, to even begin to tackle that puzzle, we need a new tool. We need a way to count that invisible flow. And in physics, we have a name for that. It's called electric flux. And really, all it is, it's just a way of measuring how much of an electric field is piercing through a surface. So to get our heads around this, let's start super simple. The simplest case imaginable, really. Take a look. We've got a single positive charge, we'll call it Q, just sitting inside this imaginary sphere. And its electric field lines, they're radiating out in all directions, kind of like rays from the sun, and they're all piercing right through that spherical surface. And that's our electric flux. It's really just a count of the total number of those field lines poking through the surface. The easiest way to think about it is just total outflow. You got more lines piercing the surface, that's a higher flux. Fewer lines, you guessed it, lower flux. Simple as that. All right, so far, so good. But here's where it gets really interesting. When physicists actually sat down and calculated the total flux in this super simple setup, something completely unexpected happened. Seriously, this is where the magic begins. Now, there's a bunch of calculus involved in the calculation, but don't worry, we're going to skip right over that, because what matters is the answer. And the answer boils down to this incredibly simple, beautiful little formula. The total flux is just the charge Q that's inside, divided by this fundamental constant of nature, this little Greek letter called epsilon naught. That constant just, well, it connects the field to the charge that's making it. And this is the big aha moment. Check out this quote. The most remarkable thing is that the flux is completely independent of the size of the sphere. Think about that for a second. It means it doesn't matter if our imaginary sphere is the size of a pea or the size of the sun. The total outflow, the total flux passing through it is exactly the same. That's wild, right? So you're probably asking, how is that even possible? Well, this is why. As you make the sphere bigger, yeah, the electric field gets weaker further out. But at the same time, the surface area you're measuring over gets way bigger. And it turns out these two things cancel each other out perfectly. It's this beautiful balance. Just look at the image. Every single field line that pokes through that tiny inner sphere has to, by definition, also poke through the giant outer one. The total count just doesn't change. Okay, so size doesn't matter. That's a huge clue. But what about the shape, right? What if our imaginary boundary isn't some perfect, beautiful sphere? What if it's just some weird, random, lumpy blob? And this is where it gets even crazier. Get this. The shape doesn't matter either. It's completely irrelevant. As long as that charge is trapped on the inside, you can draw any closed surface you want around it. A sphere, a cube, a blob that looks like a potato, it doesn't matter. The total number of field lines piercing that surface, the total flux, will be exactly the same. Okay, but wait, what happens if the charge is outside our blob? Well, look at this. Any field line that goes in on one side has to come out on the other. Every single one. So the amount going in is perfectly balanced by the amount coming out. The inflow cancels the outflow. And the net result? The total flux is just zero. And you know what? The same thing happens if the total charge inside adds up to zero. Let's say you have an equal positive and negative charge inside. Sure, field lines flow out of the positive one, but they loop right back and dive into the negative one. So again, the net outflow from the whole surface is zero. And this is leading us to the absolute key idea here. The only thing that matters is the net charge you've trapped inside your surface. So by piecing all this together, size doesn't matter, shape doesn't matter, outside charges don't matter, we've pretty much figured out the whole law for ourselves. So now it's time for the grand reveal. Let's state it formally. And there it is, Gauss's law.
All it says is this: the total electric flux flowing out of any closed surface you can possibly imagine, and we give that imaginary surface a special name, a Gaussian surface, is simply equal to the total net charge you've enclosed inside it divided by that little constant. That's it. It is that profound and that ridiculously simple.
This image just nails the concept. If we want to find the total flux through that big surface S, what do? We completely, 100% ignore all those charges on the outside. Forget them. All we care about are the ones trapped inside, so we just add them up. Q1 plus Q2 plus Q5. Sure, those outside charges might bend the field lines a bit, but they don't change the final in versus out count. Not one thing. So what's the big deal? Why is this law so incredibly powerful? Because it's a shortcut. It lets us completely bypass unbelievably complicated calculations. It takes what could be a nightmare of a physics problem and turns it into simple arithmetic. It's not about calculus anymore. It's just about counting. I mean, look how easy it is to apply. Step 1, you draw any imaginary closed surface you want. We call it your Gaussian surface. Step 2, you just add up whatever charge is inside that surface. Step 3, you divide it by that constant. And bam, that's it. That's the flux. All the messy details, like where exactly the charges are or the wacky shape of your surface, they just vanish.
All right, let's do a couple of quick-fire examples to see this in action. Look at the blue surface on the left. What's the total charge inside? Easy, it's just +2 microcoulombs. Done. Now look at the red one on the right. The charge inside is -2. The shapes are totally different. Who cares? The process is exactly the same.
Okay, let's try one that looks a little trickier. We've got this lumpy surface, 3 charges inside, 2 charges outside. So, what's the plan? First rule of Gauss's law: ignore the stuff on the outside. They're just noise. Then, we just add up what's on the inside. So, we've got a +6, a -4, and a -1. So, what's 6 minus 4 minus 1? It's just +1. The total net charge is just +1 microcoulomb. See? All of that apparent complexity, the multiple charges, the weird shape, it all just boiled down to a single, simple number. That is the power of Gauss's law. Now, this whole amazing law kind of depends on one tiny little assumption, that any surface you draw actually has a clear inside and a clear outside. But what about a shape like this? This is a Klein bottle. It's this bizarre mathematical object that actually folds back through itself. So it technically has no inside or outside. It only has one surface. Kind of breaks your brain, right? And that sets us up for one final thought. See, the genius of Gauss's law, its magic, is that it forces us to change our perspective. It tells us, hey, stop focusing on every little detail at every single point in space. Instead, just look at the total flow across a boundary. And when you make that radical shift, all the complexity disappears and a beautiful, simple truth is revealed. And that has to make you wonder, right? What other fundamental truths about our universe, what other elegant simplicities are just hiding in plain sight, waiting for us to find the right perspective to see them?